everyone. Welcome to the second lecture of the course Mathematical Aspects of Biomedical Electronic System Design. We are studying the module Signals and Systems, and today in this second lecture we will learn about Fourier Series. To elaborate, we will learn about continuous time periodic signals, continuous time Fourier series, properties of Fourier series, and similar things, same concepts for discrete time signals as well. So let us begin with today's lecture. Okay. So let's begin with looking at what are periodic signals. A continuous time signal x t is called periodic with period t if xt plus capital T is equal to xt for all t. Okay. Moreover, if xt is periodic, then smallest capital T, such that the above equation holds, that is xt plus t is equal to xt for all t, is called fundamental period of x. Notice that fundamental period is a period of xt, and any integer multiple of fundamental period is also a period of x. Here are examples. Let us consider x1t equal to cos 2 pi over 3 t. Observe that x1t is periodic with period. So let's see. If I compute x1t plus 3, it becomes cos 2 pi by 3t plus 3, which is x1t. So x1 is periodic with period 3. Actually 3 is fundamental period of x1 in this case. Let's look at another example. Say x2t is sine pi by 10t. As in case of x1, we can verify that x2 t plus 20 is x2t for all t. x2 is periodic with period 20. So here is a question. Suppose x1t and x2t are periodic. Is the sum of periodic signals also periodic? Question. Is the sum of periodic signals also periodic? Okay. More precisely, if x1 is periodic, with fundamental period t1, and x2 is periodic with fundamental period t2, is x1 plus x2 periodic? Here is the answer. x1 plus x2 is periodic if and only if t1 by t2 is rational. Okay. Notice that if t1 by t2 is rational, then there exists integers n1 and n2 such that n1 t1 is equal to n2 t2. In this case, say this is equal to t, then t is period a period of x1 plus x2. Okay. In fact, in this case, least common multiple LCM of t1 and t2 is the fundamental period of x1 plus x2. Of x1 plus x2. Let's see examples. In the above example, we saw that x1 was periodic with period 3 and x2 was periodic with period 20. Then their least common multiple, that is 60, which period of x1 plus x2. In the above example, x1 plus x2 is periodic with let's see, in the above example, t1 by t2 is 3 by 20, which is rational. So x1 plus x2 is periodic with fundamental period 60. However, let's see another example where x1t is cos 2 by t. So its fundamental period is 1. x2t is cos t. What is its fundamental period? Its fundamental period is 2 pi. t1 by t2 is not rational. So this time x1 plus x2 is not periodic. Okay. Having seen periodic signals, let us now also recall the notion of complex exponentials. Let us recall complex exponentials. Recall that xt equals to e raised to st, where s is a complex number, is called a complex exponential. So these are complex exponentials. Notice that if s, the complex number, is sigma plus j omega, then e power st is e power sigma t into e raised to j omega t which in turn is e power sigma t times cos omega t plus j sin omega t. Here this, sorry, j sin omega t here this sine and cos functions, they constitute the periodic part. So this is a periodic signal, these are, whereas this is envelope of complex exponential. Okay, now this periodic signal is called a sinusoid. So formally, a signal of the form cos omega t plus phi, or say sin omega t plus phi, is called a sinusoidal signal. It's called a sinusoidal signal. Okay, so what we see that in exponential, complex exponential can be written as a weighted sum of sinusoidal signals. A complex exponential can be written as a weighted sum of sinusoidal signals, we can say. On the other hand, if I take any sinusoidal signal, let's say cos omega t plus phi, this can be written as e j omega t plus phi plus e minus j omega t plus phi divided by 2, which in turn can be written as e j phi by 2 e j omega t e minus j phi by 2 e power minus j omega t. Right, so now we see that we can write a sinusoidal as a weighted sum of complex exponentials. Right, so we see that interchangeably we can write complex exponentials as weighted sum of sinusoidals and vice versa. Right, so for this region, so now we have sinusoidal signals. Let me write it clearly. Sinusoidals as weighted sum of complex exponentials. So one can be represented in terms of others. For this region, we also refer to weighted sum of complex exponentials as weighted sum of sinusoidals. As weighted sum of sinusoidals. Okay. With this notion in mind, let us now look at what a Fourier series is. Fourier series represents a periodic signal as a weighted sum of sinusoidals. A periodic signal as a weighted sum of sinusoidals. Okay, particular, let us consider xt a periodic signal with fundamental period t fundamental period capital T. In this case we call omega naught equals to 2 pi by capital T to be the fundamental frequency of xt. Call to be the fundamental frequency of xt. Frequency of xt. For xt we can represent it as xt to be weighted sum of complex exponentials or weighted sum of sinusoidals as follows: ak e raised to jk omega naught t. Okay, this series on the right is called Fourier series. This equation itself is called synthesis equation. Okay, it's called synthesis equation because it synthesizes a periodic signal from sinusoidal components. Okay, notice that xt is equal to a naught plus a1 e raised to j omega naught t plus a2 e raised to j omega naught t plus dot dot dot, and then there are other terms: a minus 1 e raised to minus j omega naught t plus a minus 2 e raised to minus 2j omega naught t plus dot dot dot. In this expansion, the first term, which is a constant, this is called DC term or DC component. These two terms are called first harmonics. They are called first harmonics since they oscillate at fundamental frequency omega naught. Similarly, these terms are called second harmonics and so on. So these two are first harmonics, these two are second harmonics. Okay. Let's take an example. Let xt be 1 plus half cos 2 pi t plus sine 4 pi t plus 2 by 3 cos 6 pi t. Okay. We can write these sinusoidals as weighted sum of complex exponentials and can write the whole thing as half plus 1 by 4 e raised to j 2 by t. And the corresponding other term will be e raised to minus j 2 pi t. Here we will have 1 over 2j e raised to 4 pi t minus 1 over 2j e raised to minus j 4 pi t plus 2 by 3. So this will become actually 1 by 3 e raised to j 6 pi t, and then there will be one more term 1 by 3 e raised to minus j 6 pi t. So we see that this signal xt has a DC term. These are first harmonics, second harmonics and third harmonics. Okay. In this example, a naught is half, 1, a1 is 1 by 4, which is same as a minus 1, a2 is 1 by 2j, which is negative of minus, it's negative of a minus 2. a3 is 1 by 3, which is same as a minus 3. Okay. In general, these terms akh are called Fourier series coefficients of xt. In general, akh for k equal to 0 plus minus 1 plus minus 2 etc. in the expansion in the Fourier series of xt are called Fourier series coefficients of xt. Before we proceed, let's see a couple of important properties of Fourier series. Properties of Fourier series. We will see more properties as we go along. Okay. So the first property is, if xt has Fourier series coefficients ak, then x star t, which is complex conjugate of xt, has Fourier series coefficients a star minus k. So let me write it. If xt has Fourier series coefficients ak, then let's say x hat t, which is x star t conjugate of xt, has Fourier series coefficients bk equals to minus, rather a minus k complex conjugate. Okay, so this property is called conjugate symmetry property. Property. Okay. The other property is, and it follows from the first one, it says that if x is real valued, if xt is real valued, and has Fourier series coefficients ak, then ak is equal to a star minus k. Okay. In particular, this says that if xt is real valued, we only need to compute ak for non-negative k, and we can recover or we can retrieve ak for negative k from these values. Okay. So next point is, given a periodic signal xt, how do we find Fourier series coefficients ak for xt? Finding Fourier series coefficients. So given xt with period t, rather fundamental period t, let me write it, fundamental period t and fundamental frequency omega naught, omega naught equals to 2 pi by t. The Fourier series coefficients are obtained using the formula ak is 1 over t 0 to t xt e raised to minus j k omega naught t dt. Now this equation that gets Fourier series coefficients from the signal itself, this is called analysis equation. Notice that the integrand in this equation, that is xt e raised to minus jk omega naught t, is periodic with period t. So rather than integrating it over 0 to t, we can integrate it over any interval of width t and we will get the same coefficient, same outcome. So we can also define ak to be 1 over t naught to t naught plus t xt e raised to minus jk omega naught t dt for some t naught. So this is alternate definition of Fourier series coefficient. Okay, let's see an example. So example that we take is of periodic square wave. So here is the example. So it's a square wave with period t. So this is 0, t minus t, and the square pulse width is 2t1. So this is minus t1 to t1. This will be t minus t1 to t plus t1 and so on. Okay, so clearly this is a periodic signal with period t, and the coefficients can be computed as follows. E0 will be 1 over t minus t1 to t1 dt, which gives 2t1 over t. Similarly, for k not equal to 0, ak will be 1 over t minus t1 to t1 e minus jk omega naught t dt, which if we work out, it turns out to be 1 over k pi sine 2 pi k t1 over t. Let's see another example, and this time we look at triangular wave. So wave consisting of triangular pulses. It's called periodic triangle wave. It looks as follows. The height of the triangular pulse is 0.5. On the other hand, its period is 1. Okay, we can compute the Fourier series coefficients for this wave following the similar procedure as for the square pulse above, and it turns out that, for instance, A0 will be simply the area under this, the average value of this, right? So minus 0.5 to 0.5, and before I compute it, let's also see that this mathematically This wave can be written as follows: xt equals to 0.5 minus modulus of t for all t in minus 0.5 and 0.5, and then it repeats with period 1. So with this in mind, with this in view, I can write a0h minus 0.5 to 0.5 1 by 1, which is the period, and here it will be 0.5 minus modulus of t dt, and this turns out to be equal to 0.25. If we compute coefficients for ak for k not equal to 0, we find that ak is equal to 1 over 2 pi square k square 1 minus cos pi k, which is equal to, since 1 minus cos pi k is 0 when k is even and 2 when k is odd, it turns out to be 0 if k is even and 1 over pi square k square if k is odd. Okay, so this is how we compute Fourier series coefficients. Now let us look at a more fundamental question. In particular, let us recall the definition of Fourier series. Recall Fourier series definition. We define Fourier series for a signal xt to be k equals to minus infinity to infinity ak e raised to jk omega naught t. In writing this, we assume that the series on the right hand side converges. Well, but the question is, does this series converge? In particular, I mean that if I define a signal xmt to be, in other words, if we define xmt to be a finite sum where I only take terms between minus m and m, so ak e raised to jk omega naught t, then as I take m to infinity, does xmt approach xt? Okay, so this is the question that we would like to answer, because the very definition of Fourier series relies on convergence of this. Okay, we answer this question by the following theorem. So here is the theorem. Suppose we make two hypotheses. Suppose x is periodic with fundamental period t and fundamental frequency omega naught equals to 2 pi by t. This has been the standing assumption all through. And the second hypothesis is x is piecewise linear piecewise continuous with piecewise continuous derivative, Under these hypotheses, if x is continuous at a point t, if x is continuous at t, then the limit that we would have liked to exist indeed exists. So limit m tends to infinity, xmt is equal to xt. On the other hand, if x is not continuous, at t, then also not everything is lost. Then if it has left hand and right hand limits, left and right limits, x t minus and x t plus, limit m tends to infinity, still the sequence xmt converges, but it converges to the mean value of this left and right limits, xt minus plus xt plus. Okay, so let's see a couple of examples. Let us again go back to the triangular wave example that we saw just a while ago. Triangular wave signal. Notice that for this signal, xt is continuous everywhere. So the above theorem implies that Fourier series converges at each point. The theorem implies that the Fourier series converges at each point. On the other hand, if we see the rectangular wave signal, here we see that xt is either 1 or 0 or there is a jump. Okay, then the above theorem implies that limit m tends to infinity xmt, it will be same as xt, that is 1 if xt is 1, 0 if xt is 0, and it will be half of 1 plus 0, that is half if t is a jump instant, right? If t is a what we call jump epoch. Okay, so this is about convergence of Fourier series. Let us now see a few more properties of Fourier series. We have already seen a few properties of Fourier series. Okay, so the first property says that if there are two signals x and y with identical periods and they have Fourier coefficients ak and bk, then Fourier coefficient of a linear combination of x and y can be written as a linear combination of Fourier coefficients ak and bk. To be precise, let's see, if xt and yt have same period, I would say the same fundamental period, xt has Fourier series coefficients ak, yt has Fourier series coefficients bk, then alpha xt plus beta yt will have Fourier series coefficients alpha ak plus beta bk. This property, as we can see it, it's referred to as linearity. Let's look at the next property. If xt has Fourier series coefficients ak, then the time shifted version of xt, that is x hat t equals to xt minus t naught, has Fourier series coefficients ak e raised to minus j omega naught t naught. So you see, there will be j k omega naught t naught. So we see that the time shift reflects in the exponential here. Okay, let's look at another property that's called time reversal. So this was time shift. The next property that we will see, it's called time reversal. So what does it say? It says that if xt has Fourier series coefficients ak, then x hat t, which is x of minus t, has Fourier series coefficients a minus k. Has Fourier series coefficients a minus k. To be precise, if I denote Fourier series coefficients of x hat t by bk, then bk is a minus k for all k. Okay, so this is called time reversal. The next property, well, this is a property that we have already seen, but let me put it again for recollection. If xt has Fourier series coefficients ak and xt is real, then a star k will be same as a minus k. Okay, so this is the property that we had seen earlier also, but I have put it here so that all the properties are there at one place. Finally, real and even symmetric. So what I mean by even symmetric is xt is same as x minus t for all t. Then we have ak is equal to ak star for all k. That is, ak's are real. This is obtained by combining 3 and 4. We now turn our attention to discrete time signals. So to begin with, let us look at discrete time periodic signals. So xn is called discrete time periodic with period n, and n is non-zero if xn is equal to xn plus capital N for all n. Okay, so here is the question. Is xn equal to cos omega naught n periodic for all omega naught? Answer is xn equals to cos omega naught n is periodic if omega naught is rational. Sorry, if omega naught by pi is rational. Okay, here are a few examples. Cos n, clearly 1 by pi is not rational, so this is not periodic. Cos 5 pi by 5n, what about this? This is periodic with period n equals to 10. Okay, next question. As in continuous time case, we can ask if we have two periodic signals, will their sum always be periodic? The answer is, so is sum of periodic signals periodic? Well, the answer is similar to the continuous time case. If x1n is periodic, with fundamental period n1 and x2n is periodic with fundamental period n2, then x1 plus x2 is periodic if and only if n1 by n2 is rational. And if x1 plus x2 is periodic, fundamental period of x1 plus x2 is LCM of n1 and n2. Well, we didn't define the fundamental period of discrete time periodic signals. So for that, let's see the following. Fundamental period. If xn is periodic, then we saw that so let's see, if xn equals to, let's say, cos omega naught n is periodic, then we saw that omega naught by pi is rational, so then there exist integers m and n such that omega naught over 2 pi is m by n, or omega naught into n is 2 pi m. The smallest m m, so the smallest n for which equality holds is called fundamental period of xn. So for which this equality holds is called fundamental period of xn. Let's see an example. Consider x1n to be equal to cos 5 pi by 7. Following above definition, it can be seen that x1n is periodic with fundamental period n1 equals to 14. We have already seen that x2n, if defined as cos pi by 5n, is periodic with fundamental period 10. Notice that n1 by n2 is rational. So x1 plus x2 is periodic, and its fundamental period rather is LCM of 14 and 10, which is 70. Okay, so having defined periodic signals, let us now move to definition of discrete time Fourier series. Let's look at Fourier series. As before, Fourier series expresses as sequence a discrete time signal with period n as linear combination of complex exponentials. So, Fourier series expresses a discrete time signal as linear combination or weighted sum combination of complex exponentials. For instance, if xn is periodic with fundamental period n, then we can express xn as summation of, or okay, as rather I would say xn as, we can express xn as linear combination of complex exponentials phi kn, where phi kn is e raised to j k omega naught n. Omega naught here is 2 pi by capital N, and as in continuous time case, it's called fundamental frequency. Notice that phi k plus capital N of n will be e raised to j k omega naught capital N plus small n, which will be e raised to j k omega naught capital N times phi k n, and this term is 1. Why? Because omega naught times capital N is 2 pi. So this is phi kn. So we see that there are only finitely many independent functions phi kns, right? So we see that phi kn is same as phi k plus n plus which in turn is equal to phi k plus 2n and so on, and there are only capital N independent functions namely phi 1n, or let me start with 0, phi naught n dot 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 phi n minus 1 n. Okay, so as a consequence we can represent xn as a finite sum. So unlike continuous time case where we had an infinite series, in discrete time a periodic signal xn is represented as a finite sum of complex exponentials. More precisely, I can write xkn as this. As in continuous time case, this equation is called synthesis equation. Let's see an example. Let us fix capital N to 6. Right? In this case, phi k of small n is given by e raised to jk 2 pi by 6 n. Okay, and we have already seen that for any value of small n there are only capital N independent, or rather there are only capital N independent functions phi naught n to phi 5n or phi 1n to phi 6n. Let's see how this values will look like. So k equals to 1. In this case we'll have phi complex exponential as follows. So here I have phi 1 0, phi 1 1, this will be phi 1 2, phi 1 3. So this is phi 1 2, phi 1 3, phi 1 4, and this is phi 1 5. From what we discussed earlier, phi 1 7 will be same as phi 1 1, phi 1 0 will be same as phi 1 6, and so on. Right? Similarly, if I choose k equals to 2, I get only 3 distinct complex exponentials, which are as follows. Here I have phi 2 0, then this is phi 1 1, sorry, phi 2 1, and this is phi 2 2, phi 2 3 because of periodicity will be same as phi 2 0. Right? Similarly, I can write complex exponentials for k equals to 3 and k equals to 4 as well. I leave those as an exercise. Okay. Now let's see a few properties of complex exponentials. Right? Properties of phi kn. Okay. So first thing is periodicity in n, that is phi k n plus capital N is phi k n for all n, and this is called periodicity in n. Okay. Similarly, we have phi k plus capital N equal to phi k n, and this is called periodicity in k. This is the property that we just saw. Periodicity in k. The next property is if we add these complex exponentials, n equals to, let's say, 0 to capital N minus 1, the summation turns out to be n if k is 0 plus minus n plus minus 2n etc., and it's 0 otherwise. This is a property that can be easily verified by carrying out the summation. Finally, the fourth property says that product of complex exponentials phi kn and phi mn is phi k plus mn. Okay. So next question is, given a periodic signal xn, how do we find this coefficients, Fourier series coefficients? Okay, just as we pose this question in continuous time case. So finding Fourier series coefficients. It turns out that if xn is periodic with fundamental period capital N, then ak, the Fourier series coefficients are given by 1 by n, k equals to 0 to n minus 1, xn e raised to minus j 2 pi by n kn. Notice that 2 pi by n is what we call fundamental frequency. Also, as in the continuous time case, we could change the limits of summation to any value as long as the terms in the summation are capital N. So we can sum from k equals to k naught to n plus k naught minus 1, and we would get the same Fourier coefficients, Fourier series coefficients. Okay, so this is a formula that is equally valid. Okay, this expectedly is called analysis equations. Let's see an example. Okay, so consider xn equals to 1 plus sine 2 pi by 10 n plus cos 4 pi by 10 plus pi by 4 and 4 pi by 10 plus pi by 4. Okay, notice that this signal is periodic with period 10, whereas this is periodic with period 5. So their summation will be periodic with period which is equal to LCM of 10 and 5, that is 10. So this whole thing is periodic with capital N equals to 10. Okay. Now we can see that xn can be written as 1 plus e raised to 1 over 2j e raised to 2j 2 pi by 10 n minus 1 over 2j e raised to minus j 2 pi by 10 n. This is by just writing this sinusoid in terms of first sinusoid in terms of complex exponentials. Similarly, the second term can be written as summation of the following two terms: half e raised to j pi by 4 e raised to j 4 pi by 10 n plus half e raised to minus j pi by 4 e raised to minus j 4 pi by 10. Okay, so in this special case we see that xn is equal to 1 plus 1 by 2j phi 1n minus 1 over 2j phi minus 1n plus half e raised to j pi by 4 phi 2n plus half e raised to minus j pi by 4 phi minus 2n. If we do term by term comparison, we find that this is a1, this is a minus 1, this is a2, and this is a minus 2. Alright, the rest of the Fourier series coefficients are 0 in this special case. The rest of the coefficients are 0. The rest of the coefficients are 0. Now before we go ahead, let us see the following property of Fourier series for discrete time signals. This is analogous to similar property for continuous case. The property says that if x is real, then a star minus k is ak. Okay, notice that in discrete case the Fourier series coefficients are also periodic, they repeat. So a minus k is same as a n minus k. Combining the above equalities, we obtain that a minus k is same as a star k. Okay, so this is an important property of Fourier series coefficients in discrete time case. So this is all that we have to see about Fourier series. We end this lecture by summarizing the properties of Fourier series in continuous and discrete time. So here is the summary. We have continuous time and discrete time. We saw synthesis equations and analysis equations. Very quickly, what these equations are: xt is k equals to minus infinity to infinity ak e or jk 2 pi over t small t. In case of discrete time, it becomes xn equals to summation k equals to 0 to n minus 1, or we can sum over any window, any interval of length n, ak jk 2 pi by n small n. As far as analysis equations goes, they become a small k 1 over t integral over t xt e raised to minus j k 2 pi over t dt, and in discrete case the equation becomes ak equals to 1 over n, again k equals to 0 to n minus 1 xn e raised to minus jk 2 pi by n. We see a symmetry in synthesis and analysis equations in both the cases, namely the signs of the exponents in complex exponential, they reverse. In case of synthesis equations, we have positive exponents, whereas in case of analysis equations, they become negative exponents. Okay? This brings us to the end of this chapter. Thank you.